So in 5th period yesterday, we didn't quite finish the worksheet, so I'm going to just write a few notes on it, and then I also forgot to give you guys this sheet, so you might need to print that out, so you'll have the notes and also the worksheet. Now, you don't have to print it out. You can just take notes on paper. There's not that many words, so it'll be okay if you don't have it, have a printer. All right, so we decided that we could use this difference quotient to get the average rate of change. But if we wanted to find the instantaneous rate of change, we needed h, which is basically the difference between the 2 points, to approach 0. Alright, so we just need to make a note that only when we take the limit as h approaches 0 do we get the instantaneous rate of change. Okay, so up until that point, it's always just average rates of change. Even if we do on that one 29.99999 and 30, that's still going to be an average rate of change. We have to do the limit to get the instantaneous. All right, so let's look at the notes for topic 2.1. This topic is just on finding the instantaneous rate of change. And the instantaneous rate of change, which means just like at the instant, like that specific second, how fast something is traveling. So the instantaneous rate of change at x equals a is represents the slope of the curve at x equals a. So instantaneous rate of change and slope at that point are synonymous. All right, so if you came by and got your worksheet, or you were in my 6th period and got your worksheet, you have a couple of graphs already drawn. If you don't, you can draw them with me. We're going to do 2 little coordinate planes. Okay, and then we're just going to draw a little graph. That looks a lot like what I had on the sheet. Okay, and then we're going to put a little point here on the x-axis and call it A. And then we're going to move over h units, and we're going to have another point. So think about what that point would be labeled. We started at A, moved over h units. That should be A plus h. Okay, now I'm going to go up to my axis, and I'm just going to put a little point at each of those. And I'm going to label the ordered pairs. So the ordered pair here, and this is the function f of x. So the x is going to be a, and the y should be f of a. All right, for the second one, the x coordinate should be a plus h, and the y coordinate should be f of a plus h. All right, and the first thing we're going to do is just find the slope of the line that connects those 2 points. That would be a secant line. Okay, and that's what you guys did a lot yesterday. So if we were just finding the average rate of change, that's going to be f of a plus h minus f of a, so that's subtracting the y coordinates, over, and then we're going to subtract the x coordinates. So think about what you would get if you take a plus h and subtract a from it. Right, that should just be h. Okay, so this part right here, that's the average rate of change. We'll do ROC for rate of change. But let's say we don't want the average rate of change. Let's say we want the instantaneous rate of change. So what we want is for that value of h to get smaller and smaller and smaller, where the points are getting closer and closer and closer to each other until we just have a tangent line at A. Alright, and so to make that h get smaller and smaller and smaller to the point where it's non-existent, that's when we do the limit as h approaches 0 of that expression, that difference quotient. Alright, so when we combine the difference quotient with the limit, that gives us the instantaneous rate of change. Okay, and that's what I was trying to get you guys to get from that whole thing with the guy jumping off the balloon in space. So we're going to call this one definition 1. We're going to have 2 of these definitions. Okay. And so A is the anchor point. Okay, so remember that when you think of the formula, you think of A as the anchor point. That's the value where you're finding the instantaneous rate of change, that point. Okay, we have another definition as well. So for this second definition, we're still going to have our anchor point at A, but we're going to have the other point we're just going to call X. Right? So our ordered pairs of those 2 points are going to be A and f of A, and X and f of X. Alright, so if we wanted to find the average rate of change between those 2 points, or the slope of the secant line, we would subtract the y's in the numerator and subtract the x's in the denominator. Okay, so again, that's an average rate of change. Okay, so let's say we didn't want the average rate of change. We wanted the instantaneous rate of change when it's in this form. So what we would do is we would bring these points closer and closer together until they're so close together that I get a tangent line. Now to do that, we have to use a limit. Now we don't do h on this one. There is no h on this one. So this time, what we're wanting to do is move the x closer and closer to A. So that's going to be, you're finding the limit as x approaches A. Okay, so once I get that in there, what we have is an instantaneous rate of change, another way to find it. Okay, and so we'll call this one definition 2. So on the first check for understanding, we have a function f of x equals x squared minus 4x. I'll pause it and write it down if you need to. All right, and we're going to find the average rate of change on the interval from -1 to 5. All right, so average rate of change, we do what we wrote in pink. So we are going to just find f of 5, subtract f of -1 from it, and then in the denominator, subtract 5 minus -1. All right, f of 5, we can do it in the calculator or we can do it in our head. We put 5 in for x and square it, we get 25 minus 4 times 5, which is 20. That's going to be 5. All right, f of -1, -1 squared is 1, minus 4 times -1 is positive 4, so that's also going to be 5. And then 5 minus -1 is 6. So we get 0 over 6, or just 0. All right, this next one is asking us to find the instantaneous rate of change. So we have two choices. We can do definition 1 or definition 2. I'm just going to go ahead and do definition 1. We'll practice with both of them again later. So let's find the limit as h approaches 0 of f of x plus h. Oh, it's not x. Sorry. We have a value for x is 3. So f of 3 plus h minus f of 3 over h. All right, this takes a lot of algebra to get to the answer, but we can do it. So we're going to keep on writing limit until we actually plug that 0 in for h. We can't do it right now because it's going to give us 0 in the denominator, and we don't want that. So let's go ahead and find f of 3 plus h. So that means I take 3 plus h, I'm going to put it in for both of my x's. So I'm going to square it, and I'm going to multiply it by 4 and then subtract. All right, from that, I need to subtract f of 3. So for f of 3, I'm going to plug the 3 in and square it and get 9. Multiply it by -4 and get -12. So 9 minus 12 is going to be -3. So I'm going to subtract -3 and then put my h on the bottom. Okay. All right, then it's just doing a bunch of algebra. So I'm going to square that binomial by squaring 3, multiplying these together and multiplying by 2, and then squaring h. All right, then I'll distribute the -4, and then minus -3 obviously is plus 3. Okay, then I'll combine my like terms. So I need to do 9 minus 12 is -3, plus 3 is 0. So my constants cancel out. All right, and then I'll do 6h minus 4h. That should give me 2h. And then plus h squared over h. Okay, and because they all have an h, I can divide through by h. Once I get that h out of the denominator, I can go ahead and plug in my 0, and when I do, I get 2. That's it. So what that means is the instantaneous rate of change, or the slope of that curve when x is 3 is going to be 2. All right, on number 2, we're going to write but do not evaluate an expression. We're actually going to do definition 1 and definition 2 on this one. All right, so let's start with definition 1. Definition 1 is when we have the limit as h approaches 0. All right, and then this particular one, our x value is 2, so a is 2. So we're going to find the limit as h approaches 0 of g of 2 plus h minus g of 2 over h. Okay, now we're not quite done. We're not going to simplify it, but or evaluate it, but we do actually need to plug them in. So that's going to be -1, and then in the place of x, we're going to put 2 plus h. All right, and then we're going to also in the place of x, we're going to put 2. Okay, and then you can stop. Okay, so I'll do the same thing for definition 2. So on definition 2, it's different. It's the limit as x approaches whatever value of x we want, our anchor point, which is 2. All right, and then it's of f of x minus f of 2 over x minus 2. All right, so I don't really have room over there, so I'm going to go underneath and plug in what I need to plug in. So f of x is -1 over 3x. F of 2 is -1 over 3 times 2. And the bottom, I'm just going to leave x minus 2. Whew. All right, let's look at number 3. The question is, which of the following gives the instantaneous rate of change of f of x at x equals -1? So our anchor point is -1. So look through those and see if you can find which one. There's actually 2. One is represented by definition 1, and one is represented by definition 2. Okay, so the first one is close. The problem is we don't want h to approach infinity, we want h to approach 0. So it needs to be this one. Now, the one after that is almost right, but we have a value for x that we need to plug in. All right. And then the other one is going to be this one right here. So lots of them are close, but there might be a negative sign or something just thrown out of whack. So those 2 will work. Okay, I'm going to make up another problem that I want you guys to add. All right, we'll call this one number 4. And on number 4, we're going to let f of x equal 2x squared minus 3x. A is going to ask us to find the instantaneous rate of change at x equals -1 using definition 1. Okay. So definition 1 is the one that has the limit as h approaches 0 of f of, and then what a is going to be whatever value, whatever number we're wanting to find the instantaneous rate of change at, which is -1 plus h minus f of -1 over h. Okay, so we're going to go ahead and take that -1 plus h, and we're going to put it in for our x's. Alright. From that, we're going to subtract f of -1. So when I plug -1 in for my x and I square it, I get 1, and then 1 times 2 is 2. When I put it in for my other x and multiply it by -3, I get +3. So that's going to be 5. Alright, so you guys try to simplify that one down on your own, please. Okay, so once that h cancels out of the bottom, we're ready to plug in 0, and that's just going to be -7. Okay, so that was similar to ones we did on the front. Right, and then we're going to do one kind of like that, but we are going to use definition 2. So for B, find the instantaneous rate of change at x equals 2 using definition 2. Alright, so definition 2, we're still doing a limit. This time, x is going to approach our anchor point at 2. Alright, and then it's going to be f of x minus f of 2 over x minus 2. Now, honestly, I kind of like doing this one better. There are times when we won't be able to use it, like later on and things that we have to do, but when we're finding the instantaneous rate of change at actual value, I think that, and we have to use a limit definition, I would definitely use this one. It's easier. Okay, so we are going to put in all our stuff. So f of x is 2x squared minus 3. From that, we're going to subtract f of 2. So I'm going to put in 2 into 2x squared, so that's 2 times 4, which is 8. All right, and then 3 times 2 is 6. So that should be 2. I left out an X there on that 3. Let me make it look right. So minus 3x and then minus 2. Alright, and then that's over x minus 2. Okay. So this one uses a lot of algebra too. However, to me, it's a little less tedious algebra. So I'm not going to be able to plug in that 2 for x until I don't have an x minus 2 in the denominator, because right now it's just going to give you 0 in the denominator. So the only way we can get rid of that whenever it's a rational expression like this is to factor the numerator, and hopefully the x minus 2 will cancel out. And it does. So this factors, the numerator factors to 2x plus 1 and x minus 2. The x minus 2 does cancel. We get the limit as x approaches 2 of 2x plus 1. And since that denominator canceled, I can go ahead and plug it in. So 2 times 2 plus 1 is going to be 5. All right, so at that point, the slope of the graph is 5. Okay, so your assignment is to do that worksheet. And we're going to keep on talking about this kind of stuff for a while, so don't panicking on me.